Good morning, everyone. Today I'll be proving the Cantor's theorem using the diagonal argument. So first, starting with what the Cantor's theorem statement says, the statement mentions that if 0, comma 1, yes, okay, starting with good morning, everyone. Today I'll be proving the Cantor's theorem using the diagonal argument. So first, to begin with what the statement says, is that if you take the open interval 0, comma 1, there can't be a bijection from the set of all natural numbers, which is denoted as n, to this open interval 0, comma 1. If we were to write this mathematically, we would write there does not exist any function from n to 0, comma 1, reiterating that n is the set of all natural numbers, which is a bijection. Now, to prove this statement, we begin by assuming that suppose there is a bijection from set of all natural numbers to the open interval 0, comma 1. So this is called proof by contradiction. Proof by contradiction. Suppose not. Suppose there exists a function f from n to 0, comma 1, which is a bijection. This indicates that there is a one-to-one function from n to 0, comma 1, as well as there is a pre-image of every element in 0, comma 1 in the set of all natural numbers. The first statement is also known as injectivity, which is existence of a one-to-one function. And for every element belonging to the codomain, for it to have a preimage in the domain, that indicates that the function is surjective. So let's focus on the second part for now. When we say that there is a pre-image of every element belonging to 0, comma 1 in the set of all natural numbers, that indicates this specifically. One second. This statement specifically implies that we have an exhaustive list of elements in 0, comma 1. So now let's make a function which is surjective from n to 0, comma 1, because we are assuming that we have an exhaustive list of elements in 0, comma 1, open interval. Now, image of 1, natural number 1, would be something like 0. x11, x12, x13, x14, and it continues on indefinitely. Then the image of natural number 2 in the codomain 0, 1 will look like x21, x22, x23, x24, continues again indefinitely. It does not stop. Similarly, for natural number 3, it would be x0.x31, x32, x33, x34, and this again continues indefinitely. Now, this process can continue for n natural numbers, not n natural numbers, but let's assume there is a natural number n belonging to the set of all natural numbers n. So f of small n, which is such that n belongs to n, because obviously we know that set of all natural numbers is countably infinite. There would be an image like x and 1, x and 2, x and 3. There will be some x and n and continue on indefinitely. Now, since we are proving this by contradiction, let's see if we can, let's see what will happen if we construct a number, let's say b, which does not belong to the open interval 0, 1. Of clarification, now in the Cantor's diagonal argument, we assume a bijection from set of our natural numbers to all the real numbers between the open interval of 0, between 0, 1 open interval. However, then we construct a number b which belongs to this interval 0, 1, which by altering like the diagonal digits of that list. Since b differs from these real numbers in at least one digit in the list, this leads to a contradiction to the assumption that there is a bijection to begin with. Hope that helps. So now, constructing b such that b does not belong to open interval 0, 1. Now, B takes the form like 0 B1, B2, B3, continues indefinitely. Now, we'll define it in such a way that we'll put B1 equal to 4 if X or A11, X11, okay. If X11 is not equal to 4. And we'll put B1 equal to 7 if x11 is equal to 4. This would mean that at any point, if we are comparing the number b, it would be this b with the image of 1. It would be dissimilar because of the dissimilarity in the first digit of the number b after decimal, which is that at any point B1 will not be equal to F1 because they differ at the first digit. As you can see, whenever x11 is 4, B1 will be something else, which will be 7, and x11 when it is not equal to a 4, B1 will be 4. This argument specifically is referred to as the diagonal argument given by George Cantor. And this argument is used to show that there cannot be one-to-one correspondence between the set of all real numbers and integers. Now, we continue this process for the rest of the digits belonging to B. We just do it for the 2 and we'll see how the process will take shape given the two examples. So we did this for B1, now we'll do the same thing for B2. We put B2 equals to 4 if x22 is not equal to 4, and we put B2 equals to 7 if x22 is equal to 7. Now we continue this indefinitely, and at some point we'll arrive to the conclusion that Bn will not be equal to some x and n. Okay. Now this first step implies that B1 is not equal to f of 1. That means the image of natural number 1 is not equal to the number b, and this implies that image of 2 is not equal to b2. Then, when we see this, we can say that bn is not equal to f of n. This implies b does not belong to the image f with for any n belonging to set of all natural numbers. Hence, this contradicts that F is a bijection. Why? Because we just proved that F is not surjective. This implies that our assumption that F into 0, comma 1, a bijection was false. Hence, 0, comma 1 is uncountable. And this is the proof for Cantor's theorem using the diagonal. Thank you.